In this video, we are going to be talking about eigenvectors and eigenvalues, which come up when we look at linear transformations from a vector space into itself, or in other words, square matrices. So before, you have seen many different types of linear transformations, such as rotation or shear transformations. So in general, linear transformations can have many different effects on vectors. But sometimes the effect can be very simple, such as just stretching a vector by some constant factor. For example, say we have this matrix A and this vector x. And if we multiply them, we see that we get 4, 2, which is just 2 times the original vector. So this transformation A just stretched the vector x by a factor of 2. And it is cases like these which we will study in this video. So now the main definition. Suppose we have some matrix A and a non-zero vector x. If the matrix A simply stretches the vector x by a factor of lambda, or in other words, ax equals lambda x for some scalar lambda, then we say that x is an eigenvector of A corresponding to the eigenvalue lambda. So in this example, we would say that x is an eigenvector of A corresponding to the eigenvalue 2, because all A did is stretch x by a factor of 2. And notice that only square matrices can have eigenvalues, because the input vector x and the output vector lambda x have the same dimensions. So just as an intuitive example, imagine you had the linear transformation in R2 that rotates vectors by 90 degrees counterclockwise. This transformation would not have any eigenvalues or eigenvectors because there is no vector where it is the case that the rotation simply stretches it. Obviously, since the vectors are rotating, they're never going to end up in the same direction as they started in. Now, let's see why we require eigenvectors to be non-zero. If you look at the equation ax equals lambda x with 0 for x, then that just simplifies to 0 vector equals itself, which is always true. So if we allowed eigenvectors to be the 0 vector, then the 0 vector would be an eigenvector of every matrix. And furthermore, it would correspond to any possible eigenvalue. So since we don't want that to happen, we just ban the 0 vector from being an eigenvector. However, the scalar number 0 can be an eigenvalue, which would mean ax equals 0x, or just the 0 vector, for some non-zero x. In other words, x is in the null space of the matrix A, and it is a non-trivial solution to the homogeneous equation, which we know implies that A is not invertible. So if 0 is an eigenvalue of some matrix, then that matrix is not invertible. So let's do an example. We have a 3x3 matrix here, and we want to see that 4 is an eigenvalue. So what would that mean if this is true? That would mean there is some non-zero solution to this equation, ax equals 4x. And so we can move the 4x to the other side and write ax minus 4ix, where I is the identity matrix. And then we can factor out the x to get this equation. So if lambda equals 4 is an eigenvalue of the matrix, then this equation has some non-zero solution. Or in other words, the matrix A minus 4i has a non-trivial solution to its homogeneous equation, so it's not invertible. So let's write out this matrix, which is just subtracting 4 from all the entries on the diagonal. And then if you row reduce it, you get this matrix. And it's easy to see that this matrix has a free variable. So the equation does indeed have a non-trivial solution. And at this point, you know that 4 is indeed an eigenvalue of the matrix. But we can go one step further and find an eigenvector corresponding to this eigenvalue. So from the row-reduced matrix, we can see that x3 is going to be a free variable, and x1 equals negative x3, and the same thing for x2. So an easy answer would be 1, 1, negative 1. And if you test it out, you see that A times this vector does indeed equal 4 times itself. So this is an eigenvector of A corresponding to the eigenvalue 4. Okay, so we looked at a specific example. Now let's go back to more general terms. So suppose we found some eigenvector x corresponding to eigenvalue lambda for some matrix A. Now the question is, can we use this eigenvector we have to find other eigenvectors corresponding to the same eigenvalue? And it turns out to be pretty simple. All we have to do is take some multiple of that vector. Say we take 4x. And then you can move the 4 outside since it's a constant. And we know that ax equals lambda x. And if you just switch the 4 under lambda, you see that 4x is also an eigenvector corresponding to lambda. So we can get infinitely many eigenvectors by just taking different multiples of x. So there are many eigenvectors corresponding to the same eigenvalue for any matrix. You might even say that there is a space of eigenvectors corresponding to the eigenvalue. Okay, so we know that any eigenvector corresponding to this eigenvalue will satisfy this equation. And then just like in the example we did, we can move this to the other side to get this equation. Any eigenvector corresponding to lambda is in the null space of the matrix A minus lambda I. Or another way to put it, if lambda is an eigenvalue of A, then A minus lambda I is not invertible, because it has non-trivial solutions to the homogeneous equation. And we call the set of solutions to this equation the eigenspace of A corresponding to the eigenvalue lambda. So notice how we defined the eigenspace as the set of solutions to this equation and not simply the set of eigenvectors corresponding to lambda. So what is the difference between these two definitions? And the key thing to note is that the set of solutions to this equation includes the zero vector, whereas if we just said the set of all eigenvectors, then that would not include 0 because 0 is not an eigenvector. And so including 0 in this eigenspace makes it a vector space, which we would want because the name has the word space in it. So you can think of the eigenspace as the set of all eigenvectors corresponding to some lambda in addition to the 0 vector. Okay, so we have a matrix A, and we want to find a basis for the eigenspace corresponding to lambda equals -5. And so by definition of eigenspace, we want all solutions to this equation, or in other words, the null space of A plus 5i. And so we get that by just adding 5 to all the entries along the diagonal, and then we can row reduce it to easily find these solutions. So we see that x2 and x3 will be free variables, and x1 is negative x2 minus x3. And so the general solution looks like this. And these two vectors will be the basis of a eigenspace corresponding to negative 5. So if you take any linear combination of these vectors, then you'll get an eigenvector that will get stretched by a factor of negative 5 if you put it through this matrix. And since we have two vectors in a basis, this eigenspace corresponding to negative 5 is a two-dimensional subspace of a 3. So visually, the eigenspace would be a plane in three-dimensional space. And any vector in this plane would simply get stretched by a factor of negative 5 if you plugged it into the linear transformation. Okay, so in general, it can be very hard to find exactly the eigenvalues of any matrix. But for a triangular matrix, which means either upper triangular, where everything below the diagonal is 0, or lower triangular matrix, where everything above the diagonal is 0. For those two special types of matrices, the eigenvalues are just going to be the numbers along the diagonal. So for this matrix A, it's upper triangular, so we easily see that the eigenvalues are going to be 1, 3, and 2. And to see why, notice what happens if we look at the matrix A minus 2i. Then this spot here on the diagonal is 0, and you can easily see that the columns are now linearly dependent. You can add up the first and second columns to get the third. Or more specifically, you would take negative 2 times the first column plus 1 times the second column to get the third column. So the columns are linearly dependent, meaning this matrix is not invertible, which means 2 is an eigenvalue. And you can see how the same thing would happen if we did a minus 1i or a minus 3i. We would have a 0 on the diagonal, which means the columns would be linearly dependent. So that's like a rough outline of the proof of this theorem. Okay, and the last theorem, say we have some eigenvectors of a matrix A corresponding to distinct eigenvalues. So each of these m eigenvectors has a different eigenvalue. Then this set of eigenvectors is going to be linearly independent. And you can see why this has to be true in the case where we only have two vectors. So say we had two eigenvectors which corresponded to different eigenvalues, but they're linearly dependent, meaning they're constant multiples of each other. Now we know that if we have an eigenvector and we multiply it by some constant, we get another eigenvector corresponding to the same eigenvalue. But that would mean our vectors essentially correspond to two different eigenvalues at the same time, which makes no sense. So they cannot be linearly dependent. Okay, so now let's go through the proof of this theorem. We are going to use a proof by contradiction, which means we assume that these vectors are linearly dependent, and we have to find some sort of logical contradiction. We know that if a set of vectors is linearly dependent, then one of them, let's call it v sub p1, is a linear combination of the ones before it in the list. So some combination of vectors 1 through p add up to p plus 1. Now, if we say that vp plus 1 is the first vector in this list, which is a linear combination of the previous ones, then that means v1 through vp must be linearly independent. And we'll need to use that fact later on in the proof. Now we're going to multiply both sides of the equation by the matrix A. And then we distribute it. Since these are all eigenvectors, we can easily evaluate the product. A times v1 is just going to be lambda 1 v1, and so on. And then we take this first equation here and multiply both sides by lambda p plus 1. And the last step is to subtract this equation from this equation, obtaining this. And here comes the contradiction. So you can see here that this is a linear combination of v1 through vp equaling 0. And we know that v1 through vp are linearly independent, which means all these coefficients must be equal to 0. But lambda 1 minus lambda p plus 1 cannot be 0 because these eigenvalues are all different. And same for this term as well, and all of the other terms that are lambda something minus lambda p plus 1. So that means all of these c's must be equal to 0. But then, if we go back to our first equation, that means vp plus 1 equals 0. But that cannot be because this is an eigenvector, and eigenvectors cannot be the 0 vector. So that is the contradiction, which implies that our original assumption that the vectors are linearly dependent was wrong. So they must be linearly independent. And that completes the proof. Okay, so example. How many distinct eigenvalues can a 5x5 matrix have? So this is just a direct application of the previous theorem. Because we know that however many distinct eigenvalues we have, the corresponding eigenvectors must be linearly independent. So for a 5x5 matrix, the eigenvectors are going to live in a 5. So if we had 6 distinct eigenvalues, then that would mean 6 corresponding linearly independent eigenvectors. But that is not possible because we can't have more than 5 linearly independent vectors in a 5. So the maximum number of distinct eigenvalues must be 5. And we can generalize this to an n by n matrix. They can only have at most n distinct eigenvalues, because a set of linearly independent vectors in a n can be at most n vectors long. Okay, next example. We have this matrix A, and we want to find eigenvalues and corresponding eigenvectors without actually doing any calculations. So just by looking at the matrix. Now, one way to do this is to see that the columns are linearly dependent, because you can add column 1 and column 2 to get column 3. This means the matrix A is not invertible, which means that 0 must be an eigenvalue. And as an corresponding eigenvector, you could just choose anything that is in the null space, for example 1, 1, negative 1. Because column 1 plus column 2 minus column 3 is the 0 vector. Now another possible answer is lambda equals 6, because if you plug in the vector 1, 1, 1, you will get 6, 6, 6. And this is a special case of this problem. If you have a matrix A in which the row sums are all equal to the same number s, then s is going to be an eigenvalue of A. So here the row sums are all equal to 6, and 6 was an eigenvalue. So this is true because the vector 1, 1, 1 is always going to be an eigenvector, corresponding to this eigenvalue s, because A times 1, 1, 1 is always going to be equal to s, s, s. Now the last example, show that if A squared is the 0 matrix, then the only eigenvalue of A is 0. So first we just start out with the definition of an eigenvalue. So suppose we found some eigenvalue of this matrix A, lambda, and a corresponding eigenvector. Now we want to show that lambda must be equal to 0. So first we are going to multiply both sides by A to get A squared equals a times lambda x. Now since the problem tells us a squared is the zero matrix, on the left side we just have the zero vector, and then on the right side we can move lambda out, and we know that ax is just equal to lambda x. Overall we get the zero vector is equal to lambda squared x. Now this last equation implies that either x is 0 or lambda squared is 0. And x is not the zero vector because it is an eigenvector which cannot be 0. So lambda squared must be 0, meaning that lambda is 0. And this completes the problem because we showed that if A has an eigenvalue, then that eigenvalue must be 0.